everyone, welcome back. This is Miss Graham, and we are going to be looking at Lesson 7-3, Perpendicular Lines. You should have out pages 84 through 86 in your textbook. Today, we're going to look at developing theorems to show that lines are perpendicular. Then we're going to determine whether lines are perpendicular. So if we zoom out and look at the margin at the left side, we can see that two lines or parts of lines are perpendicular if they intersect to form right angles. It also talks about a story problem here. It says a second customer of Patios by Madeline has hired the company to build a patio with a row of bricks that are perpendicular to the walkway as shown at the right. So over here we can see we have our walkway, which I'm highlighting in red. And we can see that we're creating, we have that row of bricks that's perpendicular to it. I have that in yellow. Perpendicular means it creates 90-degree angles. So we can see that we have a real-life situation where we can apply perpendicular lines. We're going to skip numbers 1 and 2 and focus on our new vocabulary of these different postulates that we can bring into our proofs. So if we look at the margin at the left, it says the perpendicular postulate states that if given a line and a point not on the line, then there is exactly one line through the point that is perpendicular to the given line. So let's just draw a picture of this. So they're saying, let's say we have a line and we have a point not on the line. It says there is exactly one line through this point that is going to be perpendicular to the given line. So let's see if I can best draw this. So this is what it's saying. There's one line exactly through the point that can create a perpendicular relationship. Let's continue to look at the one below. It's the parallel postulate. It states that if given a line and a point not on the line, then there is exactly one line through the point that is parallel to the given line. So let's draw a picture like the one above. So let's say we have a line, all right, and let's say again we have a point not on the line. It says there is exactly one line through this point that I can draw that will be parallel to that given line. So let's go ahead and draw that. Not exactly the straightest, but that's okay. We can understand the idea how both of these are going to be parallel lines. So that's the perpendicular postulate and the parallel postulate. Let's go ahead and go to our next page because remember, we are skipping numbers 1 and 2. On the next page, again, we're not going to look at numbers 3 and 4. What we're going to do is we're going to look in the margin. So if I zoom into the margin, I can see I have another definition that I'm working with. This one is focusing on the perpendicular transversal theorem. So it says the perpendicular transversal theorem states that if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. Let's go ahead and draw this type of visual. So we have a transversal that's going to cut through two parallel lines. All right, so let's start off drawing maybe our two parallel lines. And I would definitely want to put that symbol that shows they're parallel. Remember, it's that triangle, or if you like just putting the arrow, you could also put the arrow. Either way works. And then we have our transversal cutting through, let's try drawing that again, cutting through the parallel lines. And we know that transversal is perpendicular to one of the parallel lines. So this theorem states that, it must be perpendicular to the other one as well. Hey, this is starting to look a little bit like some of the other pictures that we've seen over the past couple of days. You've probably seen something labeled where each line is labeled a letter like M or N, and maybe our transversal is labeled L. And we have to go ahead and show maybe the different relationships between these lines, maybe given certain angle relationships. That's what we're going to be focusing in on today. We have one more definition we're going to be looking at, and we're going to go ahead and skip down to the bottom where it says a perpendicular bisector. So a perpendicular bisector of a segment is a line or part of a line that intersects the segment at its midpoint to form right angles. So again, we're going to draw a picture to help us out with this. So we're going to start off drawing a segment. Let me go ahead and grab my pen. There we go. We're going to draw a segment. Now, sometimes I like drawing segments completely horizontal or completely vertical, but I also think it's realistic to do angled ones as well, so you can get a better understanding of what we're looking at. All right, so we have our segment. Now, our perpendicular bisector. It can be part of a line. It can actually be just the segment of a line, but it's going to intersect this segment at its midpoint to form right angles. So let's say I label the segment we have as AB. And let's say I create another segment. We're going to call that CD. So I know that CD is going to be our perpendicular bisector because it creates a 90-degree angle with segment AB, but it also divides segment AB at its midpoint. So point D is going to be the midpoint. So segment AD and DB will be congruent to each other. So again, in this case, the perpendicular bisector is going to be CD. So something we can kind of keep in mind. And we know point D is going to be at the midpoint of segment AB. Now, remember, for each of these, we have to make sure we put that segment across them because we're not looking at measurements. We're labeling segment CD and we're labeling segment AB. We're going to go ahead and practice some more problems together. So go ahead and turn to page 86, the midpoint. So on page 86, we're going to start looking down at the bottom at numbers 9, maybe possibly 10, 11, 12, and 13. Let's see how far we get. Let's start looking at number 9. So I'm going to do number 9 in the margin over here. So we have some background information. It says in the diagram, L is perpendicular to M. All right, so I'm going to go ahead and I'm going to start putting those markings on there so that way I know L is perpendicular to M. That's given information right here. It also tells us the measure of angle 1. The measure of angle 1 is 90 degrees. Oh, so I know that's a right angle. I can make that marking right there. Again, you could also put 90 degrees, but we know that symbol means the same thing. It also tells us, that angle 5 is a right angle as well, so that also measures 90 degrees. It says use the diagram to help answer items 9 through 11. So let's look at question number 9. It says explain how you know that L is perpendicular to P. Well, think about this. We know the measure of angle 1. Angle 1 measures 90 degrees, so it is a right angle. Because lines L and P intersect to form a right angle, then they are perpendicular. So let's start off writing that. So we know angle 1 measures 90 degrees, so it's a right angle. And we know because lines L and P intersect to form a right angle, then they are perpendicular. So right now, we're not necessarily doing proofs, but we're going through that logical reasoning, that thought process that helps us lead up to proofs. Let's go ahead and let's look at number 10. So it says, show that the measure of angle 4 is 90 degrees. Okay, so we want to show that the measure of angle 4 right here is 90 degrees. Well, let's start off thinking. We know that L is parallel to M. And we just proved prior, right, in number 9, that L is perpendicular to P. So we must know line M must also be perpendicular to line P. That goes back to that idea of a perpendicular transversal theorem. Remember, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. So we would probably say something along the lines of, because of the perpendicular transversal theorem, we know that M is perpendicular to P since, remember, L is parallel to M, since L is parallel to M, and remember what we explained in number 9, L is perpendicular to P. L is perpendicular to P. That's just starting off our problem, thinking of how M is perpendicular to P. Now, we want to think about how perpendicular lines intersect to form right angles. So let's write that down. So perpendicular lines intersect to form right angles. So that must mean angle 4 must be a right angle and must measure 90 degrees. So we're going to say, so angle 4 must be a right angle and measure 90 degrees. And that's exactly what we're trying to show. The measure of angle 4 equals 90 degrees. Let's go ahead and look at number 11. Number 11 says, show that line L is perpendicular to line N. Well, this is a little tough because we haven't had any information about line N yet. So maybe we kind of have to start thinking ahead a little bit. What are some pieces of information we know? Well, think back to what we were given up here. We know the measure of angle 1 is 90 degrees, and we know that angle 5 is a right angle. So technically, we know angle 1 and angle 5 are both right angles, so they have to be congruent. Let's start by writing that information down. So angle 1 and angle 5 are both right angles, so they are, let's try again, they are congruent. Now, think about why I'm looking at angle 1 and angle 5, right? That's starting to look at the relationship between line L and line N. I'm trying to make some connecting point there. Think about what another relationship is between angle 1 and angle 5. So start thinking about that. Pretend like line M isn't even there at all. See if you can identify what that other relationship is. So if you notice, they are also corresponding angles. So we could bring up that relationship. They're congruent and they're corresponding angles. So we're going to say angle 1 and angle 5 are also corresponding angles. Now remember, corresponding angles, they are formed by two lines with a transversal cutting across from it. We don't necessarily know if they're parallel, but we can make that statement that they are formed. So we know angle 1 and angle 5 are also corresponding angles formed by lines L and M and cut by a transversal. So we have to think about what that means. Well, think back to what we looked at yesterday. We started looking in lesson 7.2 at the converse of some certain theorems and postulates. Think about the corresponding angles postulate. We said that if two lines are parallel and cut by a transversal, then corresponding angles are congruent. we're going the opposite way. Do you see how we're using the converse of the corresponding angles postulate? That means we're saying if corresponding angles are congruent when two lines are cut by a transversal, which is exactly what we said, then that means the two lines must be parallel. So what we're going to say is by the converse of the corresponding angles postulate, we know that L is parallel to N. Again, the purpose of going through each of these problems is for us to start that thinking process, for us to see what information do we have and how can we prove another idea. Now, let's go ahead and look at number 12. All right, so number 12 says the perpendicular bisector of CD. Oh, okay, so we're going to have to draw our own picture for this. So we have segment CD, and it says the perpendicular bisector of it intersects CD at point P. So let's imagine, let's try that again. Let's imagine a perpendicular bisector, and it's going to be at point P. Maybe we have, a ray going the other way, okay? So think about this. If this is the perpendicular bisector, remember it creates a 90-degree angle. CP is going to be congruent to PD. So it says if CP, it says if this whole length is 12, what's the length of this whole piece? Well, that's easy. Remember, we know CP is congruent to PD, so both of these are going to be 12. So altogether, we are going to get 24 down here. So our length should be 24. So we're going to say CD is 24. Now remember, we don't put the line on top of that because we're looking at an actual measurement. So we can write units if that helps us out. All right, I think that's a really good review and practice of lesson 7.3 today. So what I'm going to have you do is you don't really have any required homework, but I did post a table of definitions, properties, postulates, and theorems that it would be really good for you to review. And I also posted some optional practice from activity 6 and activity 7. I have the answer keys on there as well, so you can kind of check your work. I know some students were asking for some extra practice going over the properties, our theorems, our postulates, along with setting them up in a proof format. And some students were also looking at how to identify angle relationships. So we're going to look at angle relationships again tomorrow, but today go ahead and check out the calendar for some extra optional practice.